Welcome to the lecture series of network theory. In my next few classes, I will be discussing about the sinusoidal steady state response of RLC network. Now this part will be divided into 6 classes. First I will start with RL circuit, then it will be followed by RC circuit and then RLC circuit. And every type of circuit will have again 2 classes. One is for series circuit and the other one is for parallel circuit. Today I will start my class with series RL circuit. We will see that what are the expressions of instantaneous current and voltage in case of series RL circuit, how to derive them, and what is the phase angle between current and voltage in case of series RL circuit. We will also solve numericals based on the concept that we will be learning today. So let's get started. First, we will start with a pure inductive circuit where we have only a single inductor, as you can see in this circuit, which is energized by a AC voltage source having value V. And suppose this AC voltage source is supplying AC current I. Now this small v and small I, these are the representations of instantaneous values of voltage and current respectively. Now suppose if we take the current as a reference, and since this AC supply is sinusoidal in nature, so the current that it will supply will be also sinusoidal and in nature, and that current if we take as reference, then that can be written as I is equal to Im sine omega t. Now sine omega t, it represents that it is a sinusoidal signal or waveform, and Im here is the maximum value or peak value of the AC current flown through that inductor, and small I, as we know, that represents the instantaneous value of that current. So if we put the value of t, or suppose the value of any instant, then we will be getting the value of that current at that instant. Now if we want to know that what is the voltage drop across that inductor, which here we are representing as VL, then that value, as we know, that can be found by this formula. VL will be equal to L di by dt. Di by dt is the rate of change of current that flows through that inductor. So here L, and in place of I we have replaced that I by this expression Im sine omega t, and that we are differentiating with respect to again time. So if we differentiate, then finally we will be getting this value. From this Im is constant with respect to t, so it will be L multiplied by Im, and sine omega t, if we differentiate, that will give us cos omega t, and this omega will come out as per the rule of differentiation. So finally it will be omega Lim cos omega t. Since this expression is an expression of voltage, and as we know that the supply voltage that we here applied, that is sinusoidal in nature, so the current that was also sinusoidal in nature, and the voltage that will be dropped across this inductor, that will be also sinusoidal in nature. So from this expression, what we will do is we will represent this cos in terms of sine. So cos omega t, finally if we represent in terms of sine, then it will be sine omega t plus 90. Since it is positive omega t, so here it will be omega t and plus 90, since in the second quadrant we know that the value of sine is positive. So it will be, as per the rule of trigonometry, it will be sine 90 degree plus omega t, or we can arrange this way, omega t plus 90 degree. And since the expression or the format of the voltage and current is like this, the peak value of that term, when it was current, it was Im, then sine omega t. So here it will be sine and this angle. So before that, whatever we have, that will be the peak value of the voltage. So in place of omega Lim, we are here representing by this Vm. So the expression of the voltage drop across this inductor will be Vm sine omega t plus 90 degree, where Vm is the peak value of this induced voltage or AC induced voltage across that inductor. Now from this expression of this voltage drop, the points that, or the conclusion that we can draw is, first, this Vm, the peak induced voltage across that inductor, will be equal to omega Lim. So that has been written here, omega Lim. Now Im is the maximum value or peak value of the current flown, and omega L, in place of omega L, we that term we can replace by XL, and we have already learned in our previous class that this XL is the inductive reactance, and that value is omega multiplied by L, where L is the inductance of that inductor and omega is the angular frequency, which is expressed in radian per second. And since this is the relationship between voltage and current, and that is in terms of peak value, so when we will express this in terms of RMS value also, root mean square value, that will be again that they will hold the same relationship. So it will be VRMS, that will be equal to XL multiplied by IRMS. Now since the relationship between RMS and maximum value is this, RMS is equal to peak value or maximum value by root 2, so the maximum value of voltage or current will be equal to root 2 times the RMS value of that quantity. So in place of Vm, if we write root 2 multiplied by Vrms, and in place of peak current, if we write root 2 multiplied by IRMS, then root 2 and root 2 on both the sides will cancel each other. So on both the sides we will have, on the left side we will have Vrms, and on the right side we will have IRMS. So the relationship which is true for peak value, that is also true for RMS value. In case of purely inductive circuit, what we can see here, that the current, when we took that as reference, that was expressed as Im sin omega t, and we can also think this way, omega t plus 0. So here the phase angle is 0 degree, and when we have derived the voltage drop across that inductor, we got this type of expression Vm sin omega t plus 90 degree. That means between the voltage drop across that inductor and current flown through that inductor, there is a phase difference of 90 degree, and this positive 90 degree or positive phase difference, it represents that the voltage leads the current by 90 degrees. So in the phasor diagram, if we take this quantity as current, then this will be our voltage, and in anti-clockwise direction if we move, then this is the measurement of 90 degree. So as per this, since voltage leads current by 90 degree, so this will be the phasor diagram of a purely inductive circuit. We can also draw the circuit like this. If we take or draw this way, then voltage across that inductor can be drawn this way. Both are same. So here horizontally we are drawing current, and then in anti-clockwise direction if we move by 90 degree, then it will be the voltage drop across that inductor. So we can also say that current lags voltage by 90 degree, but this is true only for purely inductive circuit. But with that inductor, if we have a resistor connected in series, that doesn't work as a pure inductor, rather it will be an impure inductive circuit, or we can say series RL circuit. And in that case, in case of series RL circuit, the phase angle or phase difference between voltage and current is not, or is no more 90 degree, rather it is less than 90 degree, and that we will see next. Now if we see the graphical representation of those waveforms of voltage and current, here as we can see, this red waveform represents the current and blue waveform represents voltage, and this is the point where x-axis or horizontal axis and y-axis intersect. So this is the origin 0, 0. So since we took in the previous slide when we derived that current we took as a reference. So here at the origin, the waveform, here also we have taken current as reference. So when time is equal to 0, the current waveform, we can think this way, the current is starting. But with respect to current, as we can see, when the current is minimum at t is equal to 0 or omega t is equal to 0, the voltage already has some value, and that is the peak value or maximum value. That means the voltage has started before current, and voltage, as we can see, has started here. So from this also we can say that the voltage is leading current. And as we can see here, for the positive half cycle of the current waveform, this is the point where it enters into the negative cycle, and this measures 3.14. Now we know that the relationship between degree and radian is pi radian is equal to 180 degree, and pi we approximated as 3.14. So 3.14 radian will be equal to 180 degree. And we know for a sinusoidal it is a periodic waveform. So for a complete period, it actually angularly it completes 2 pi radians. So for the half cycle it will be pi radian, and that will be 3.14. So on this scale, on this horizontal scale, it is represented in terms of radians. So it is 3.14, and when it will complete the negative half cycle, so it will be measurement of 2 pi. So it will be 3.14 multiplied by 2. That means this point will be around 6 point, or approximated value will be 6.28. Now on the other side, if we see that the voltage when it starts, this is around minus 1.57, and if 3.14 radian is equal to 180 degree, then minus 1.57 will be 180 degree by 290 degree. So between this point when the current waveform starts and this point when the voltage waveform starts, the phase difference is 1.57 or 90 degree. Now next we will see a series RL circuit, and we will derive the expression of voltage. Here this R and L are connected in series, and we are energizing that series RL circuit by an AC voltage V. And suppose that AC voltage supplies AC current I. Now if again, since I is the current which flows through R and L, the same current, since they are connected in series, so same current flows through both of them. That's why here the I again has been taken as a reference. So I is written as Im sine omega t, where Im has the same meaning. It is the peak value of the current that flows through that series RL circuit. Now the instantaneous voltage drop across the resistor will be, say if it represented as VR, then VR simply it is the resistance part, so it will obey Ohm's law. So V will be equal to current that flows through that resistor multiplied by the resistance value. So it will be simply IR. R is constant, the value of that resistance, and I is Im sine omega t. So this is the instantaneous voltage drop across the resistor. And now if we assume that the instantaneous voltage drop across the inductor is VL, then VL is equal to L multiplied by di dt, rate of change of the current flows. Then L, and in place of I we can replace I by Im sine omega t, and if we differentiate, then as we have seen in the previous case for purely inductive circuit, it will be omega L Im cos omega t. Now if we replace cos by sine, then it will be sine 90 degree plus omega t, or we can rearrange this way, omega t plus 90 degree. So these are the instantaneous voltage drop across resistor and inductor. Now if we want to get the total voltage across that series RL path, then it will be simply VR plus VL. So this value are Im sine omega t, and that will be added with this value. So omega L Im sine omega t plus 90 degree. Now what has been done here, R Im sine omega t has been written as it was, and this sine omega t plus 90 degree, this has been expanded following the formula, as we know that it is sine, if it is A plus V, then we know that is sine A cos B plus cos A sine B. So just that has been followed here. So if omega t is assumed as A and 90 degree as V, then omega L Im that was already there with this sinusoidal term. So omega L Im and then sine A cos B plus again omega L Im, then cos A, this is A, plus cos A means cos omega t, and sine B, so sine 90 degree. Now if we put the value of cos 90 degree and sine 90 degree, cos 90 degree we know that value is 0, and sine 90 degree that value is 1. So simply this term will vanish and this term will be omega Lim cos omega t. So finally the total value or total instantaneous voltage drop across that series RL branch or path will be Rim sin omega t plus omega Lim cos omega t. Now this is the value of the voltage. So if we now draw the phasor diagram between voltage and current of this series RL circuit, then it can be drawn this way. Say the voltage, say the current which is common for resistor and inductor, if we draw that first as we took that as reference, then this is the phasor of the current, and then we will draw the phasor of the voltage drop across the resistor. And since only for the resistance or resistor the voltage drop and current will be in same phase, the phase difference between the voltage across a resistor and the current that flows through the resistor, that we have already seen in one of my previous lectures, that the phase difference is zero for purely resistive circuit. So when we will consider only the resistor or resistive part and the voltage drop across that resistor, then the between VR and I, the phase difference will be zero. That means if we draw the phasor of VR, it will be simply in the same phase. That means it will be a line parallel to I. So it will be a line parallel to that current. So this is the phasor of VR. Now we know that in case of purely inductive circuit, the voltage drop across that inductor, it leads the current by 90 degrees. So if now we draw the phasor of the voltage drop across that inductor, then between that VL, voltage drop only across the inductor, and the current that flows through that inductor, which is same since this is a series branch, between them the phase difference will be 90 degree. So the voltage phasor will be like this. Between that VL and the current, it will have 90 degree angle. So this will be the phasor of VL. Now if I draw this VL here, a parallel line to that dotted line which represents, so this will be our VL. And now if we take the resultant of these two, VR and VL, then this will be our V, the total voltage drop across that series RL branch. So this is our V. Now this is the total voltage across that series path, which is V, and this is the current which flows through that series path. So between this V and this I, as we can see, there is a phase difference, and that phase difference is not exactly 90 degree, rather it is less than 90 degree. But still, since this is an inductive circuit, though it is not pure, but still it is an inductive circuit, so here also the voltage will lead, and that's what we can see from the phasor diagram, that voltage is leading the current. But the phase difference is not 90 degree, rather it is less than 90 degree because of this resistive part. So now if we, the total voltage drop, if we represent by the sinusoidal waveform following that expression, then that can be written as V, the maximum value of that voltage, which is Vm, then sine omega t, and since here the phase difference between the total voltage V and the current is theta, and V is leading, so it will be plus theta. So this is the expression of that voltage or total voltage across that series RL. And already on the right side we have this expression Rim sin omega t plus omega Lim cos omega t. Now next, if we expand this term again, sin A plus V, so we will get this type of expression where Vm, then it will be sin A means sin omega t cos theta plus Vm cos omega t sin theta, and that will be equal to this term or the summation of these two terms that we already have in that equation. Now as we can see here in this equation, on both the sides we have sin omega t term, here also we have sin omega t, and on the right side also we have sin omega t. Similarly, on the left side we have cos omega t, and on the right side also we have cos omega t. So if we now equate the coefficients of the like terms, like for sin omega t, here on the left side the coefficient is Vm cos theta, and from the right side the coefficient is RIM. So if we equate the coefficient similarly for the cos omega t also, then the relationship that we will get, so it will be Vm cos theta will be equal to RIM, and from the other part, from the cos omega t, then it will be Vm sin theta, that will be equal to omega Lim, and that has been written here in the next line. Now next will our task is to find out the value of that phase angle which is not 90 degree. So here what has been done is we have just taken the square value of both the sides of both the equations. So it is Vm cos square theta, and it is Vm square cos square theta, and it is Vm square sin square theta, and then we have added. So finally Vm square cos square theta, and since Vm is common, so within bracket it will be cos square theta plus sin square theta, which gives us 1. So finally, after addition on the left side, we will have only Vm square term, and from the right side we will have R square Im square. So it is RIM square plus omega Lim, that square value, and straightforward we have calculated here the Vm value. So it is simply the square root of this summation of those individual square terms. Now from these two terms, as we can see, Im square, that value is common, so that has been taken common from this expression, from this summation. So Im square, and then finally we have the square root, so when it will come out, then it will be Im only. So Im then multiplied by within square root, we have R square plus omega L square. Now since this is the maximum of peak value of the voltage, and so it will follow the Ohm's law, and that will be Im multiplied by the impedance value. Since it is not a purely resistive circuit, otherwise it would have been resistance, Vm would have been Im multiplied by the resistance value, but since it is an AC circuit where along with resistance we have inductance also, so it will be inductive impedance or impedance of that RL path. So here in place of resistance, it will be simply Im multiplied by the impedance of that series RL path, and the value of that impedance will be nothing but this. So this is the value, and now we can also say that or we also know, we have seen in our previous class that impedance of an inductive circuit or impedance of a series RL circuit is represented as a R plus j omega L, and this imaginary part basically is contributed by the AC component, and this is the resistance value. So now this is, we know that this is a rectangular representation, and if we convert this to its equivalent polar representation, then it will be simply R square plus omega L square and the square root. This is the R value, and in the polar representation we have this format, R and then some angle theta, and that angle, how it is represented, tan theta is equal to the imaginary value divided by the real value. So theta will be tan inverse, then the imaginary part we have, in the imaginary part we have omega L divided by the real, in the real part we have R. So theta value will be simply tan inverse omega L by R. So this is the polar representation of the impedance value, and this is the rectangular representation of the impedance value. So here the theta value is tan inverse omega L by R. So this is the value of the phase difference between the total voltage of that RL path and the current that flows through that RL path. Here in the previous line where we have represented the peak value of the voltage in terms of peak value of the current, then if we want to find out the peak value of the current in terms of peak value of the voltage, then we can do this way. Im will be equal to Vm by Z, then Vm by Z is R plus j omega L, and this is rectangular representation, and I have already discussed that when we do multiplication or division, then it is easier to do that, to multiply or divide, if we represent in polar form. So if it is not already in polar form, then first the rectangular form, or the data that which is represented in rectangular form will be first transformed into polar form, and then we do the rest of the calculation. So first, since we are dividing here by the Z value or impedance value, so this rectangular format first will be transformed into polar format, and this is what we have already seen here. So this is the value. Now this is r part and this is theta part. So it's simply here we have Vm. So we can also think this way, that Vm and angle is 0 degree. This is the reference value. So for any quantity what we are taking as reference, the phase value is 0 degree. Now Vm and this value, the r value, they will be this Vm will be divided by this value simply, and angle wise, since we are dividing here, so it will be subtracted. So from 0 we will be subtracting this angle value, so it will be finally minus tan inverse omega L by R. So this is the value of the peak current which we are expressing as or in terms of peak value of the voltage. Now previously when in the for pure inductive circuit or for this RL circuit also, we started with current. We took current as reference and then we expressed voltage in terms of current. So since current was taken as reference, so sine omega t, and since in case of purely inductive circuit the voltage leads current by 90 degree, and for impure inductive circuit or RL circuit there also voltage leads current but it is less than 90 degrees, so we expressed omega t plus theta. In other way also we can express, like if we take voltage as reference, like if we this way we express that V is equal to Vm sine omega t. So here we are taking voltage as a reference. This is the instantaneous value and this is the peak value. So current with respect to voltage, we know that the current will lag voltage, and for RL circuit it will be the current will lag by theta. So the current that will be expressed in terms of when voltage has been taken as reference, it will be expressed like Im sine omega t then minus theta, that phase difference. So here that's what has been shown here, that I is Im sine omega t minus theta when voltage has been taken as a reference. So Im, the value of Im has already been found out. This is the value and this is the phase the measurement of phase difference. So this is the value, and since we are expressing by this sine and omega t minus theta, so theta part, that phase difference part, we are already incorporating here. So that's why we are not separately showing that phase angle here, rather we are including that theta value or phase difference value in within that sine term. So the finally the I, the instantaneous value of the current, can be shown this way, where this Vm by this value will be the measurement of Im, the peak value of the current. So this is the explanation of series RL circuit in when we take current as reference, then how we represent voltage, or when we take voltage as reference, how we represent current, how we represent those terms in phasor diagram, how we can find out the impedance value. Now next we will see the waveform representation in terms of waveforms. Now here again the current has been taken as reference. So this is the origin where this x-axis or along which we have represented the angle or omega t value, and this is the y-axis along which we have represented the amplitude of voltage and current, and this is the origin. So since current was taken as reference, so current is starting at the origin, and this is the peak value of the current when the omega t value is 1.57, then current is at its peak. And with respect to current, as we can see, when current is just starting, voltage has already progressed to some extent. That means voltage has started before current. Voltage has started here, but this time it is not 1.57. Previously, when it was purely inductive circuit, we have seen that the difference between voltage and current was 1.57 as per the scale that we took on x-axis. It was 1.57, so that measures pi by 2 angle, but here it is less than even -1. So that basically between this point and this point, this is the phase difference, which is theta in degree, that is theta degree, and in radian it is somewhat which is less than -1. So here graphically also we can show that between current and the voltage the phase difference is less than 90 degree.